Hi, this is a video on Lesson 1, Module 6, kind of talking about ion formation. So just to kind of get you thinking, so if we were to write magnesium's electron configuration, it would be 1s2, 2s2, 2p6, 3s2. So in order to become stable, like a noble gas, which we call the octet rule, they want to have a full valence shell, and you can see that there are a full 8 electrons right here. So what magnesium wants to do is really lose these two 3s electrons. So in order to become like a noble gas, it will lose 2 electrons, and then it would become electron-like neon. It doesn't become neon, but its electrons are like neon. So when we have an ion being formed, we have to put in ionization energy, and then we do get the ion, and we write that symbol for the charge as a superscript, plus we get the 2 electrons. So the charge is always, if it loses electrons, it will be positive however many electrons it loses, because the protons don't change, so you end up with more protons than electrons. Here's another one we can just start thinking on. So this is sulfur. So sulfur, we can do this one as a noble gas configuration. Either way, it doesn't matter. So then it would be 3s2, 3p4. So you can see that sulfur has 6 valence electrons, and it's really going to want to change this 4 to a 6, and then it would have 8. So neon is going to want to gain, not neon, sulfur is going to gain 2 electrons. So then that would change this to a 6, and then that would actually change it into argon, argon's electron configuration. So when we have a negative ion being formed, we're adding electrons, and then we form the ion, which is an anion. Charge is equal to however many electrons were gained. And we have a new type of energy. This is called electron affinity. So we'll keep going. So the octet rule, we know this. They want, atoms want to be stable. Usually they end up with S2p6, which would be 8 electrons. So a chemical bond is just what holds a mutual attraction between atoms that holds it together. So when you're looking at an ionic compound, like this would be representing sodium chloride. Yellows are the sodium ions, cations. Greens are the chloride or the anions. So they're attracted to each other because they have opposite charges. So we can also talk now again about ionization energy. If you remember, ionization energy is the energy needed to remove one of the outer electrons. And now electron affinity, this is new. So this is just the opposite really of ionization energy. It's how much energy will get released when an atom gains an electron. So it's also, just think of it as how much would an atom be able to attract an electron to itself. So my question, I guess, to think on is, do metals have high or low ionization energy, and do they have high or low electron affinity? So metals, remember the trend, they have low ionization. They do want to get rid of their electrons, because if they do, then underneath those valence electrons would be the octet of electrons. And they also have a low electron affinity because they don't want to gain electrons, they want to lose electrons. Nonmetals are going to have, if you remember, a high ionization. They don't want you to take off their electrons because they're already really close to having their octet, and they have a high electron affinity. I'm just going to say EA. So think about noble gases then. Do you think they have high or low ionizations energies, and do they have high or low electron affinities? So noble gases are going to have really high ionization energy. It's nearly impossible to remove an electron because they're already very stable. And they have low electron affinities. Again, they have no interest in gaining an electron because they already have the octet that they need. So a cation, when we do get, like we did with magnesium, a cation is when the electrons were lost and you end up with a positive ion. So let's do another one here. So let's do calcium, and then we'll do noble gas this time. So calcium is argon electrons plus 4s2. So it's going to lose those 2 electrons, so then it will have the same, this is really the calcium ion now, but it has the same electrons as argon. And then the symbol, remember, is going to be with that ion charge as a superscript. Transition metals are going to be positive. They still want to lose their electrons, like every other type of metal, and they can sometimes have charges that are +3 or greater. And we do get these what we call pseudo-noble gas electron configurations. So for example, zinc. Zinc is, I'll write the longhand. So zinc is in the D block, and what'll happen is it will lose these 2 electrons, its valence electrons, but it's going to keep its D electrons. So therefore, it's really the same electron configuration as argon, but with the D. That's why we call it pseudo. It's not like the ones I just showed you where they become an electron exactly like a noble gas. They're still going to have some D electrons left over. So anions are negatively charged. This is when we gain electrons, because now you're going to have more negatives than the protons, because the protons don't change. And let's do this one together. So let's do oxygen. So you can see it has 6 valence electrons, right? Sorry, I'm trying to highlight here and here. So it wants to gain 2 more. So then it would become 1s2, 2s2, 2p6, which is like neon. You can write it either way. If you do the neon way, you want to use the brackets. And then because it gained 2, it's -2 charge. And I think that's it. So let me go down. This is the kind of what went the worksheet that went along with the reading. Let's just do one thing you can do is skip the one that says silver, and let's do the gallium. So this one is a little weird, but here's your valence electrons. Remember the highest N, which N is 4, S and P electrons. So it will lose those, and then it'll end up being electron like argon with those D. So this is an example of a pseudo noble gas. So the symbol, because it lost 3 electrons, is going to be +3, and this is a cation. And that is